the following outline. So, and I'll first talk about symmetric group. So after which I will talk about the reduced word counting formula for certain permutation, which I'm going to introduce. After that, I will talk about some connection. So first connection, I will talk about connection to algebraic geometry. Particularly, I will talk about the connection to the Grassmannian G2N. So this is the space of K-planes in the N space. So if you have time, also I will talk about the connection to discrete geometry, where we talk about dilation of the standard two simplex. Okay, so let's get started. So now by permutation, everybody knows permutation is a bijective map on the finite set. Okay, so and the set of this connection is actually called a symmetric group and is denoted by Sn. So in this presentation, I would like to, because there are many ways of writing permutation, but I will only stick to one line notation here. So if I say a permutation, you see that as W1, W2 up to Wn, something like that. So, and we know that every finite group, because Sn, symmetric group, is a finite group of order n. So every finite group has a finite presentation. It means that it has a finite number of generators and a finite number of relations. So now for our symmetric group Sn, it is generated by a simple transposition. Okay, so transposition means that a permutation of length 2, that you just swap the elements here. So generated by simple transposition subject to the following relation. The first one is talking about Si, it means that its generator is an involution. So, and the second one is a Bray relation. So you can actually use the Bray relation. So Si plus 1 Si, that would be Si plus 1 Si, what have you. And the third one is called a commutation. So we can actually try to swap if the difference between indices is bigger than 1. Now, so where do we go from here? So given any permutation, so we can talk about the length of the permutation. The length of permutation has to do with the number of inversions which you have in the permutation, and is given by this formula. So it's the number of inversions you have, and the generating function is given by this formula. So for the length generating function for the permutation given to us, so you can actually, for permutation group, so this is the generating function. Okay, so now where would this one lead us to? So if let's say that we are given, so sorry, I can't see this. One thing is blocking it up. Yeah, maybe I should bring this one down in a moment if I can do that. Oh, good. Yes, thank you. So now we said that a symmetric group is generated by a simple transposition. It means that every permutation can be written or can be decomposed into the product of simple transposition. So this decomposition is called reduce. If the product of this is if K here is of the length of the permutation. In other words, so if the product of transposition, the number of product you have equals to the length, is reduced. So reduced means that it is minimal. It can be longer. So, but the shortest one is called the reduced decomposition, and we say that that indices A1, A2 up to AK is actually the reduced word for this it's a reduced word for this permutation. Sorry. So now to be frank, or to say what the fact. So this decomposition is not unique. In other words, so we can get as many decomposition as possible because we have to just use the relation I talked about the other time. So now, for example, now if you have the permutation now in S5, so 3, 5, 1, 2, 4, so that it has 5 reduced words. So the 5 reduced words. So this is a reduced word. So I can use a commutation. So 3 and 1 here. So I can swap this, so and that will give me this, and I can use it does not have break, but I only use the commutation here. So but using commutation, I can realize 5 reduced. So we say that this permutation 35 1 2 4 has what 5 reduced word. Okay, now So, and from reduced world, we can talk about the graph of the reduced world. So, graph of the reduced world is actually given by the first. We won't talk about the graph. We talk about the vertices and the edges now. So, you see, so the reduced world constitute the vertices for this graph, while the edges. So, we said that two vertices are joined by an edge if there is a relation between the two. So like this one now, so 4, 2, 3, 1. So if I change this one, so I can change the 4, 3, 1, so that there is an edge here. So that is how to talk about about the graph of reduced world. So you use a relation to constitute edges and reduced world to constitute vertices for the graph. So this is the graph of 35 or the permutation 35, 1, 2 in S5. Good. Now, so if let's look at this permutation in S6. Now I have 6, 5, 4, 3, 2, 1 now. So it has 64,064 reduced word. So it is, so it's not that when we talk about reduced one, they might be very huge. They may have as many, we have a big number of them. So now the question that is important now is that given any permutation, so how can we compute R? In other words, so what will be the number of reduced word? So unfortunately, there is no closed formula for this. Okay, we don't have a closed formula for this. So if you have a permutation that there's no closed formula that will say, okay, this is the number of reduced word we are going to get. But the question is that why is it important? Why do we have to talk about the number of reduced word? Because that number encodes a lot of information. Okay, for certain permutation in geometry, so one can use this number, this cardinality to actually discuss, to compute the degree of Grassmannian, and that one has been done. So I think that one has been done. So, and also it has a lot of combinatorial information. So that's why people are actually interested in knowing what's the number of reduced. But unfortunately, there is no, as I said, no closed formula. But there's a formula due to Billy, I guess. So this one has to do with recursion. So you have to, it's recursive in nature. So though it is very, 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 very effective, but it is not efficient in the sense that, it is effective, it's not efficient in the sense that if you have large number now, so to do the recursive of that number, that will be very difficult. So we don't have closed formula that can actually do the work. But for certain permutations, so like this permutation, the longest permutation, I've talked about the length now. So let's look at the longest permutation in Sn. That would be n minus 1, n minus 2, up to 1. Now, this is the longest permutation in Sn. So that is the notation. So Stanley gave this formula as the number of reduced word. So if it's in we're an S4 now, that would be 4, 3, 2, 1. We have 16 of them. Okay, so this is the formula. And if you look at it closely, for some of us who actually understand the combinatory of a standard tableau, so this is actually the number of the standard tableau. The number of standard tableau that you can realize from this partition. So it encodes a number of information. And this number that we are looking at, also for some of us who are familiar with representation theory, this has to do with the number of irreducible representation of a permutation module. So, and it's very important because of a lot of information that people can realize from this. Now, my case is that now this is what Stanley gave us. So I consider this permutation of this nature. So we have a permutation like this in Sn for n bigger or equals to 4. So we have the permutation of this form. So now for n equals 4, so we are looking at a 4, 3, 2, 1. N equals 5. That will be 5, 1, 3, 2, 4. So n equals 6. You have that. So as n grows, so it becomes very visible that it satisfies the form that we are looking at. The question is that how do we count the reduced word of permutations of the class of permutation of this form? So that is my interest. Why am I interested in it? Because of the connection of this permutation to geometry, to algebraic geometry, and also discrete geometry. So so that we have to look at number of properties for this permutation. So the first is that the length is actually n plus 1. So for the first one, 4321 is of length 5. And also it has cycle type. So this cycle type, cycle type is hook in nature. Of course, for some of us who have the understanding of this, so it's hook in nature because you only have one part that is bigger than one. The rest just 1, 1, 1. So the cycle type is n minus 2, 1, 1. And one also see that number 3 is telling us that the consecutive fixed point that we have there actually occur at position n minus 2 and n minus 1. If you look at for the position n minus 2 and n minus 1, that is where we have the fixed point. In this case now, so this will be 1 goes to 4, 2 goes to 2, 3 goes to 3. That is why we have the fixed point. Okay, so position n minus 2 and n minus 1. So in this case now, you have 3 goes to 3, 4 goes to 4. So n minus 2 and n minus 1. So that is the position that we have there. And it has there are only 2 descents in this permutation, in the class, in this permutation, the permutation that you have of this class. So you will see that this one has a descent here, descent at position 4, and descent at 4, and descent at what? At 5. So at position 1, and also at position 3. Descend here and descend there. So two descend. So these are very, very important because we want to actually give a formula. Let's say how can we count number of reduced word for any permutation of this form. So it is very important. And I want us to pay close attention to the length, because we will make use of this length, and also we make use of this cycle type in what we are going to be talking about. So now, now for any course, for, as I say, so there are so the partition, I mean the reduced word for this, we have 6 of them, and I will explain why I have to color some blue, black, and red later on. So we have 6 of them here. So for R equals 4, so we can actually compute that. So, but what about R equals 10? R equals 2? What about N equals 10? N equals 15? So we actually need a formula to actually do the counting, and also we need to actually understand what does this formula, what does it encode, if we have time. Now, so for the graph now, so this is the graph of 4R. So this is the structure of the graph for this. So now the first proposition is that if every reduced word inside the set of every reduced word belonging to NR, so as exactly 2 ascend and n minus 2 descend. Exactly 2 ascend and n minus 2 descend. So I will be using this example, is a baby example, to actually explain what I'm talking about. So if you look at for this one now, it has descend now. So descend at position 1, descend at position 2. So 2 descend. 2 descend here, 1 descend here, and another descend. So it has 2 descend, and I've told you that it's going to be of this is n equals 4, so it's going to be of length 5. So that's why we have 1, 2, 3, 4, 5. So we have the 5 entries for each reduced word. So you have you will see that as 2 descend and 3 ascend for each one of them. So that is very important that we understand that. So because we are going to make use of this in order to actually to do the counting. Okay. So now so in general, so this is the structure, if you of the for any hand. So this is the structure, and and I'm going to look, I'm going to talk about this the endpoints. So this point and this point and this point, that is this vertex, and this vertex. So these are the 3 cardinal points, because at this vertex, if you look at the structure of this, this is where we orientate it so that we can realize symmetry. Okay, so at this point now, so we have the symmetry as such that what we have above the line resemble what we have below the line. So it's very rich when we talk about the symmetry, and it's not strange because of the connection to certain objects in geometry, which is also which also is symmetrical in nature. Let's continue. Now, so with this now, so we are saying that the permutation that often that I talk about now, so the permutation, this permutation NW admits reduced word of the following types. So first is that we have some reduced that will start with n minus 3 but end with n minus 1. And some will start with n minus 1, end with n minus 1. And the reduced word that only end with 1. So we have been able to count that. So there will only be one of type 1, and n minus 2 of type 2, and n minus 1 choose 2 of type 3. So in other words, so if you go back here, so that is, in fact, that is the classification now. That's why I have to name this of the type 1, type 2, type 3. So we have this one now. So starting with 3 ending with 1. Okay, so there are 3 of them. You have this one now, n minus 2 of them, and this is one that actually ends with n minus 1. So this is just the only one of such. So that is classification. It's not peculiar only to this, as we'll see later on. There are this is the behavior. That's why we call it classification. So we are going to mix up this this pattern when we in our formula. So let's move on. I haven't seen that. Yeah. So okay, now in order to count. Okay, in order to count, so and this is very interesting. In order to count, I have to use a combinatorial object to count the number of reduced word. So, and the combinatorial object that I'm interested in, we call it recorder. Okay, and the recorder is it has to do with a row streak tableau. So, what my row streak tableau? So, so supposed to be tableau, sorry. So a row streak tableau of type tau of this shape, okay, is the filling of the number of Young diagram associated with this shape. So with this, with the set of 1, 2, 3 up to n like this, such that the number in the row strictly increase from left to right. I'm going to give an example of such now. So that is when we have the filling of the we have a partition like this, and then you associate to it a diagram, and you talk about filling of the diagram with numbers, boxes of the diagram with numbers. So such that number that you have in each row, they actually increase from left, they increase strictly from left to right, but you don't bother about what happened to the column. You are only interested in what happened to the rows. So if that is the case, so the question is that how do we count given a shape now, a shape lambda? So how many row streets are there? So it's given by, the number is given by what we call the multinomial coefficient. So multinomial coefficient, we count by the number multinomial coefficient. But in our own case, okay, so what we are interested in now, we are using the cycle type of our permutation essence. So this is the shape that we are interested in. Okay, the shape n minus 2, 1, 1, because we know that our permutation that we have is it has the hook shape. So we are looking at the shape of this. So and we want to look at the row streak tableau sub-collection here that will actually fit into our counting. So let's see how we go about it now. So for example now. So now this if you pick a row strict inside this list, okay. So you know that we know that this is counted by they are going to be n factorial over n2 factorial 1 factorial 1 factorial. That will be the number of them. But among them now, so we want to know which one is called recording. So we say that this style is a recording rostry tableau if the number that we have in this column, that is the first column that you have. So we are in the first column, the last two boxes that you have. So we say that they actually decrease downwardly. So for example now, for the tau, this shape, now this is shape 211, so it's throw strict. So if you look at the first column, now the last two boxes that we have, so the number there is 14. So this is not a recording tableau. But if you look at it, this is 23, but the last two columns, this is 41. This is what we call the recording tableau. So this is recording tableau, and we are going to look at the set of this later on and see what, and let us see how we are going to make use of this. So now the question is that, so if you denote, if you know by D, so Cn minus 211 to be the set of recording row street tableau, okay, of this row street, then the cardinality of it will just only be half, the half of the number of the row street that we have. For example, now I think I have example here. Yes, for example now, so now if I'm looking at 311, so 311, there are 20 row street tableau, but how many of them would be recording? So there are only 10 of them, because if you look at this, cannot be, because this one is 445, 35, 34, 24. But when we come here, we have 54, 53. So there are only, these are one in red. So these are the only ones that can actually constitute the element of our recorder. So C311 has only 10 recorders. So, and this is very, very interesting, because we are going to use this now. Now that we have the understanding, or yes, of our recorder, we know the set of recorders now. So the question now is that how do we use this to actually count our row, our reduced word? Okay, so how do we go about it? So, and that is the issue now. But before to go into that, so we want to actually see the bijection now, because we've already done the classification. We've done the classification of the reduced word that we have. So we said that some will start with n-1, end with n-1. What have you? We have the type 1, type 2, type 3. So, and this, we can now put this one in bijection with this, and that will look like this. So that this bijection for alpha here to be equal to this, so it's going to be of this type if it belongs to only type 1. So if you belong to type 1, it's going to be of this form. And then we know that there's only one. That one is in black. That one is in type. So that's the only one there. So we are going to have for the one that in type 2. So this is the nature of what's the name of the recording tableau. And I'm going to explain that one later on. So now, the one in those one in type C, so this is going to be the nature, the configuration of the recording of the recording tableau. So such that we have this condition that we have there. So, and from here now, so I have the formula, and the formula is that so if for the graph of reduced word, so of the permutation that we have here. Now, the order, when we say the order has to do with the number of vertices of the graph. So it's given by the multinomial coefficient that we have. So it's just the half of the multinomial coefficient. So it might be a bit complicated to prove, but I have example to illustrate the point now, and that is the example now. So we have three classifications here. So this type, the blue type, the red type, and the black type. And if you look at it closely now, so for this one now, so this one that we have now, so we have for 3 2, 1, 3, 4. So this will be the recording tableau. So, and let's try to see why it's going to be. How do I know that I can map this one to this one? Okay. Now the reason is that we look at the descent and the ascent. We look at descent and the ascent here, and actually see that this is what we have. If you look at this now, this is 4, 3, 2, 1 now. So there is descent on the first entry, verse 4, 3, descent on the second entry, and descent on the third entry. Okay, and that one constitutes the first row. 1, 2, 3. So now look at the but on the fourth entry there is what? There is ascent, and there is also ascent on the fifth row, and that's why we have 5, 4. Okay, 5, 4 is telling you that you have ascent at the position 4 and ascent at position 5, but you have descent position 1, position 2, position 3. So that is the interpretation that we can see. So, and this guy number 2 here goes to this, and the 3 here goes to the, and this one, there's only one, and that is what we have here. So, and that is the way to actually. So the question is that once I know the number of this, okay, being is half of multinomial coefficient, and that is because it's a bijection. So I use the bijection to actually establish what's the number for this. So in other words, if I want to count now, so this is number for this number actually count the reduce the what's name the cardinality is actually the cardinality of the reduced word for this permutation, which consider the vertex, and that's why we say that we have this bijection, and that is it. So the question now is that is there any question from here? Okay, so if there's no question, so let's continue. So now, so when we now with this now, so I'm not interested because the entries that we have here now actually keep track of ascent and descent of the reduced word that I have here. So now I focus on this. Now, what is my interest here now? So I'm interested in the reading of the reduced word that I have here. I'm interested in the reading here. So, and that is the next thing to talk about now, the reading now. So given a recording tableau inside this place, so its reading is denoted by tau W. It's obtained by listing the entries we have here, starting from bottom to top. Like this now, this is a recording tableau. Okay, recording tableau. So the question now is that how do I read this one now? So the reading is going to be from below to top. So this will be 2, 3, 1, 4, 5. That is the reading. Now, it is interesting to actually say that I can now talk about the set of readings now. When n equals to 4, so there are 6 readings there. So 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3, 2, 3, 1, 4, 2, 4, 1, 3, 3, 4, 1, 2. Now, if you pay close attention to this reading, when we discover that this reading that we have, it has only one descent, and that descent is at position 2. Okay, but you might say that what about this? I'm going to get to that one later. But if you look at this, so 1, 3, 2, 1, 4, 2, 3, 3, 2, 3, 1, 4, 2, 4, 1, 3, and 3, 4, 1, 2. We've discovered that everything that we have here as what unique descent at position 2. And when we have that, we say that, and also we can see that there's also a permutation in S4. So, and we can say that if you have permutation like this, a permutation with unique descent, it is called Grassmannian permutation. So each one of them is a Grassmannian permutation. We are going to get to that one later on. And from here now, so we now begin to, making use of this reading now, we now begin to look at the connection that we have. Okay, the first connection here has to do with has to do with geometry. Okay, so that is the first connection that I have here. So it has to do with geometry, so connection with geometry. So, and the geometry that I want to talk about now, the geometric object is, I want to talk about Grassmania. But before I talk about Grassmania, I need to talk about flag now. So if you have a vector space, a complex vector space now, okay? So I will talk about a flag. What is a flag? A flag is a chain of subspaces ordered by inclusion, okay? Such that the dimension of k step is k. So, and this is a complete flag. It's a complete flag because it contains all the dimensions. So you have the content of the dimension 0, dimension 1, dimension 2, up to dimension n. So dimension n is what is the vector space. So when we have it, when we have a flag like this, we say we have a complete flag. So we can talk about the set of such flag. So the set of such flag is called a full flag. Is denoted by this, so full flag variety. So it is denoted by Fn and C, okay, and it's of dimension n choose 2. So it is possible also to omit some choices in between, and you still have a chain. So now I can omit dimension 1, so I pick the origin, we still have a chain. So, and that is what is going on here. So in that case now, if you look at this now, so I pick alpha 1, alpha 2, alpha 3, such that we have this order. So I can have this flag. So, but if I pick a free k now, so the dimension is alpha k, may not necessarily be k. So if I have we have what is called incomplete flag, or we say partial flag. So incomplete flag, and if you look at the set of that will be incomplete flag variety, and the dimension is given by 4 that we have here. So now a special case is when you pick just only one subspace. You pick maybe of dimension 2 and look at the set of dimension 2 subspaces in Cn. In that case now, you realize what is called Grassmania. And that is a set of k spaces in Cn space. So that is Grassmanian, okay? And it's a projective variety, but I'm not going to go into that. The meaning that I can embed it into projective space, and each one of them I can do that. So for full flag variety, I can embed it into the product of projective space, but that is not the focus here. Yeah. So, but the focus here, because I want to make use of the permutations that I have now. So now to explain that there's a connection between the readings that I have and this Grassmanian permutation. So, and how do we get the connection? So the connection we are going to get that first and foremost is that we have to think about our full flag not as a projective space this time around, but as an homogeneous space. When we say homogeneous space is homogeneous space is any space that admits transitive action of a group. So there is an action of a general linear group on a flag variety, and the stabilizer of the standard flag is called the Borel subgroup. Borel subgroup just means that the group of upper triangular matrices, okay? So and that's why I can say that I can identify full flag variety with a G mod B. This is a homogeneous space, so you can see that. And also I can identify with UN mod T, because UN mod T, the UN is the group of unitary matrices. Okay, we are looking at the matrix such that it coincides with any matrix that coincides with the conjugate transpose. Okay, so you have this. So this is a unitary matrix, and it's a closed subgroup, compact closed subgroup of G. So you pick the maximum torus here, so we can also identify it with U mod T. And this is telling us something very important, that we can look at our flag variety as a compact manifold. That is what we are saying. So now from that, now I can talk about the normalizer of Tilling G. That will be the monomial matrices here. So, and from there, I can talk about the Y group, and that is the beginning of excitement. Now, the Y group of G is a normalizer of Tilling G, modulo centralizer of Tilling G. And since I'm working with general linear group, I will say I'm working with type A. And when I'm working with type A, so we say that this is finite. And it's finite, and it's a standard fact that we know that it is isomorphic to our symmetry group Sn that we talked about the other time. So the Y group or general linear group is Sn. So that is very important that would be. And this is where the permutation is actually coming in. And also, as far as our flag variety is concerned, we'll say that the Y group embed inside the flag variety at the set of torus space points. But that may be a bit complicated, but I'll just leave it like that. So where would this one give us lead us? So now we say that flag variety is isomorphic to G mod B, general linear group mod Boresov group. Now, what about Grassmannian that I talk about when you pick just only one subspace and look at the set of that subspace, the set of that subspaces, and this one is going to be isomorphic to general linear group, but mod parabolic subgroup now. Okay, that is not Boré. Boré has to do with it's a set of upper triangular matrices, but parabolic subgroup, so is given by this by this this is general form for parabolic subgroup. In fact, so this PK is parabolic subgroup, maximum parabolic subgroup. Okay, and because it actually is indexed by just only one root. Yeah. So what the question now is that what will be the Y group of this? Because the Y group of the general linear group is Sn. So the Y group of parabolic is what we call Young subgroup, and is given by and this is the order. Okay, so it is generated by transposition given by 11 here. Yes, so now where would this lead us to? And that is what I just want to say here now. So now the set that I talked about the other time, that is set that denoted by set tau, and that we call this the set of the readings of this tableau. So they actually turn out to be indexing permutations for the Schubert variety of the Grassmannian. And it's very interesting that these are exactly for the one that we did for n equals 4. So that will be the indexing permutation for G24 that we have, because we are looking at it in general. So for example now, so what I'm going to say for example now, so now when n is 4, so I have a set of 4 by 4 non-singular matrices. So the Boré is given by this, so triangular matrices here. So the full flag is given by this. So now I can talk about P1. So this is the form for the parabolic. So now the Grassmannian that I'm going to get here now. So G mod P1, this will be the set of line. This set of line, that is JR14. So but for when P equals to 2 here, so I have this. So this is G24. Okay, for P equals to 3, so this is G34. So now the Young subgroup for P1 is given by the Young subgroup for P2 given by there are four elements. Yeah. So the question here is that how do I get the other one that I was telling you now? So now we look at what we call the coset space. The coset space. So you know, in Sn now, in the Y group is assigned to Sn. Okay. So and that we have 24 of them for S4, and for Y2 that I have here. So for PW2 now, so there are 4 subgroups. So if I want to compose the coset now, distinct coset. So you are going to the distinct coset. If you look at the index, you do 24 divided by 4. The order of this one, that is 6, and this actually the 6 that I'm talking about. So these 6 that we have now, these are the what we call the minimal length representative of the coset here. So, and if you look at this one closely now, so that's where we do just the coset, the distinct coset. If you look at this, the minimal length, if you look at this very well now, this is actually the one I showed you before. Because this is now 1, 2, 3 that I talk about. Unique descent. Okay, so descend at position 2, descend at position 2, descend at position 2. So this is actually the connection. Even though in the combinatorics, this actually constitutes what the readings of my recording tableau. But much more than that, they have geometric interpretation. They are actually Grassmannian permutation. And that's why that is the link between this minimal length and also recording tableau that is the first link. And it's deeper than that. I'm just trying to paraphrase it so that actually we can actually see what is going on here. Now, number 2 has to do with, because I know we don't have much time. Number 2 has to do with the simplest connection with the discrete geometry. Okay, and this has to do with the lattice polytope. Okay, when we say lattice polytope, in fact, when we say polytope first, polytope has to do with the convex sort of a finite set. Okay, now when we say lattice polytope, we are talking about the vertices. Now the coordinates are integers. Okay, or the vertices. So that is so for the standard one, so the standard simplest, this simplest. A simplest is a generalized triangle, triangle in many dimensions. So the one that we are familiar with is 2 simplest, that is triangle. Well, we can have triangle 3 simplest, that would be tetrahedron. So, but the one that I'm interested in, when these 2. So now, for simplest now, so this will be the vertices. So we are A1, A2 up to ED are standard vectors in RD. So we take the converse all of that. So we have for this simplest. So and you sorry. So what about the dilation? So dilation just is the scaling. Yes, okay. I know the time is up. Okay, so the scaling. So that is the scaling. So the question is that we want to count. We can't now. So for this one now, so the converse of 3.2. But if I scale it now, so I scale it now by this one. I scale it by 2. So this is D2 now. So they're going to be 6. They're going to be for this one. They're going to be 6 points. So here that will be 10 points. So if I scale it by 4, that will be 14 lattice points. So and if I scale it by 5, that will be 21 lattice points. Now, the truth of the matter is that I'm going to stop now. So the truth of the matter is that all this lattice point that we have inside this place, we can count by this. All this lattice point that you have, they are actually the permutation that I'm talking about. I can put it in one-to-one correspondence with the permutation I showed to you. And this has been done. So, and I can have the graph for this, and this is sorry, I will stop. So I stop. Sorry, I stop. So let me stop. Thank you very much.
Thank you very much, Praise. Sorry to cut you off. If there's some time, maybe someone will ask a question about one of the diagrams you showed. Do we have any questions from